Homework should be finished.
I thought we were doing the homework now. What do you mean it should be finished?
Oh, before I forget, there's something, that's something. What is it for?
Yeah, I think it was. I didn't know it.
Oh God, he's writing notes on the board.
You did second edition. I think you did for 12.6. You did 1 to 27. I would have thrown in 29, so practice that when you have a chance. And for 12.7, which is the homework we're going to get today, it's 1 to 27 odd, and then do 33, 37, 39. Only for a second edition. If you're using the first edition, just go by what's in the syllabus.
So we don't have to do 31 and 35?
Not if you're in second edition.
So if you want to do more work, do a second edition.
Okay, questions on homework 13.6?
Number 41.
Second edition. What was it?
Y equals 4x plus z squared. And it's bounded by x equals 0, x equals 1, z equals 0, z equals 1.
So you want to find, I suppose, the area of this guy bounded by that. Okay. So what's the formula we're going to use?
Fx squared.
Double integral over d of the square root of
Partial of x squared.
partial with respect to x squared
Plus
plus,
partial with respect to y squared.
no,
Oh, z.
with respect to z squared.
Plus. You got it right. Okay.
And here they sort of gave you the limits, so it's just 0 to 1, 0 to 1.
Yeah.
You take the partial of this with respect to x, that's just 4. Partial of that with respect to z, that's just 2z squared plus 1. Dx dz or dz dx, so I don't think it matter much. So this is what? This is 0, 1, 0, 1, 17 plus 4z squared dx dz, which is equal to, when you integrate that with respect to x, there's no x, it's just itself. So 0 to 1, 17 plus 4z squared dz. And what's that?
So there's this.
Then there's a u substitution.
A u substitution?
No?
Well,
What?
first there's this other
Which other
integral
thing?
that says like the integral of a squared plus square root of a squared plus u squared equals some crazy thing. But before that, you'd let u equal 2z, I guess. And so you'd get
du.
So you'd get 1/2 from integral of 0 to 1.
Well, that's if you're using the formula tables. Like, how would you integrate this if you had to do everything by hand?
With great difficulty.
Yeah. But what would great difficulty involve? It's the path that you have to choose.
Going to the tutoring center and crying.
Make it 3/2 and then we'll put it in the chain.
Make what 3/2?
Yeah, the power of the entire thing.
Well, it'd be 1/2. The power would be 1/2.
When you raise it 3/2, you won't do that.
Nope, because there's a z squared in here.
Can we use trick?
Huh?
Can we use trick?
It is a trick substitution. What's the substitution?
Secant some.
Some.
tangent trig substitution.
So far.
All right, if you had a squared plus x squared, you substitute x equals a tangent theta. Remember that? And if you have a
Obviously
squared
we
minus
don't.
x squared, you
Oh,
substitute.
yeah.
I recall. There you go. Wow.
I'm so glad you're here to remind us.
Okay, this guy sort of looks like this, where your a is radical 17 and your x would be 2z. So you would say, so here you could actually do a substitution. Z is equal to radical 17 over 2 tangent theta. dz would be equal to radical 17 over 2. What's the derivative of tangent? And here, if z equals 0, then it means that your theta equals 0. And if z equals 1, then that would mean theta would be equal to tan inverse of 2 over radical 17.
How did you get to why did you put that?
Plug in z equals 1 here,
Right.
and then I solve for.
Oh, okay.
Okay, so those are the limits. So your integral becomes 0 to tan inverse of 2 over radical 17 of what? So what would in here become?
Square root of radical 17 times 10 theta.
It would be radical 17 times secant times this guy, radical 17 over 2 times secant squared. Which is actually 17 over 2, 0 to 10, inverse of 2 over radical 17 of secant cubed. Remember that guy?
Yes.
This is a horrible one, right?
Yes.
It's like the weird integration by parts where it actually
Secant-
showed up
secant
as a
squared.
question on its own on a Calc 2 final before, I think.
Okay.
Um,
Yeah.
yeah, just like 12b, compute this integral. It's all those really annoying ones.
Of course, you'd never
Right.
do something like that.
Huh?
I say, of course, you would never do something like that.
Well, I probably would on a meds paper or something. So, what was the integrals have? It's secant tangent plus ln of secant plus tangent. Huh? Was that it?
Yeah, Brian said this is easy when I say that.
It's something like that. I mean, back when I was doing Calc 2, I had it memorized. I don't know if I remember it now. But I think that's it. And so now you just plug in these guys. So it's 17 over 4 secant of tangent inverse of 2 over radical 17 times 2 over radical 17 plus ln of secant tan inverse 2 over radical 17 plus 2 over radical 17. Minus tangent of 0 is 0, secant of 0 is 1, tangent of 0 of 1 is 0, so that's just it. You guys remember how to figure out this guy?
Involves the right triangle somehow.
Yeah, you can say, alpha equals tan inverse of 2 over radical 17. So this means that tan alpha equals 2 over radical 17, which from that is opposite over adjacent, so you can actually form a right triangle with alpha. Opposite, adjacent, And the hypotenuse would be this squared plus that squared. So it's 17 plus 4. So it's radical of 21, which means that secant of your tan inverse of 2 over radical 17 is really just secant of alpha, which then is going to be hypotenuse over adjacent. So that's just 21 over 17. So this you can have 17 over 4, 2 radical 21 over 17 plus ln of 2 over radical 17 plus so something like that. Okay, other questions?
39.
What did that say? You're in the second edition?
Yeah. Here.
Okay, so this was the second edition, and so it's 39. Second edition, 39. So for this one, the setup wasn't that bad, but the integral was actually pretty annoying, and it happens from time to time. Part of the surface z equals xy within the cylinder of block. Okay, so here again we're going to use areas of double integral over d of the radical of x squared plus y squared plus 1 where d is actually just a circle of radius 1 in the xy plane. So I recommend the following, especially for those of you who move on to 392. I find it helps confusion a lot. Figure out the rectangular version before switching to polar. Oh, except the limits, yeah. You just save the limits for polar. So don't just jump the gun and try to go to polar coordinates, because then when you try to set this guy up, odds are you're going to make a mistake, statistically speaking. So first, find the partial with respect to x and plug it in here. Leave this as d. Partial with respect to x of that guy is what?
Why?
So that's just y squared plus partial with respect to x.
X.
Y is x, so that's x squared plus 1 dA. And now you can switch to polar. We know that this is just 0 to 2 pi. R goes from 0 to 1. And x squared plus y squared is r squared, so it's just the radical of 1 plus r squared times r dr, which is going to give you 1 plus r squared, so 3 over 2 times 2/3, so this would be 1/3. Yeah. Between 0 and 1, between 0 and 2 pi. Substitution, yes. U equals 1 plus r squared. You do the you finagle with it, you'll get that. So this would be 0 to 2 pi of, if I plug in 1, I would get
2 to the 3 halves.
And if I plug in 0, I just get 1, right?
Mhm.
So that's just 2 pi over 3 times. That's the answer.
So in general, should we worry about drawing these things or no? Because I got really hung up on trying to draw them.
Draw it if you think it'll help you. Like here, it tells me this. I don't need to draw that to know what it is. I know it's a circle,
Okay.
right? And I also know that drawing that will probably be really annoying.
Yeah,
That
that's,
was the really weird one.
Right? That's not one of the nice forms. That's going to be almost like a flailing butterfly sort of thing. Yeah. So if it's going to be, if both x and y are positive, it's positive, or if they're both negative, it's negative. So in like the first octant, it's going to be above the xy plane, while if you're in the second or the fourth octant, it's going to be below the xy plane. So it's going to be like flailing all over the place. So here I didn't need, I'd only draw if I think it'll really help, especially with these problems. It's not usually, these problems are usually there to test your prowess with evaluating double integrals. Right?
Okay.
They're not meant to be one of those visualization challenging things. So usually they'll tell you the functions work that you're bounded between, and it should be sort of obvious how they work together. Really, the only thing you'd have to graph is the region of projection. Right? So if they give you a bunch of curves, just graph the region of projection. Because you're just going to use that function to use this formula. You really don't need to know what that looks like. You just really want to know where is your region of projection. And if they give you several curves there, you just draw that. Right? So in this, with these particular problems, you don't, the drawing is not the emphasis at all. Other questions? Maybe on the next section, 12.6. You said number 25?
Yes, second.
Do you want me to show you table of contents?
Technology.
Where's all the camera?
That's the table of contents.
Okay, go to 12. Do a cross product. Integrate it. Okay, so we're looking at
35 and 3.6 and 13.6.
what? We just figured out how to get to chapter 12, and now you want to go back to chapter 13. Okay. 25. Find the volume of the region bounded by blah blah blah.
Find one region. I really like that.
One, blah, 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 DB.
So find the volume. Z equals x squared plus y squared. Z equals 36 minus x squared minus 3x squared minus 3y squared.
Maybe I have.
And b find the centroid.
This one is gonna be 0. The y is gonna be 0, because
So the lesson we learned from Nettie is always check what we write down for the question.
Glad I could be of service.
Z equals x squared plus y squared, z equals 36 minus 6. Copying down the question right is half the battle.
Actually, it's all of that.
For some of us, it's all the whole battle. Yeah. Damn it! Didn't see that 3. Okay, how do we find volume? Volume, we're in the triple integral section, so volume
1
is
dB.
triple integral of 1. So now we have to figure out how to set up this guy so we can actually draw a picture of what it looks like. So one is a paraboloid going up. Right. The other one is a paraboloid with 36 going down. So the object of our desire is that something that looks like this. Right? So that's going to project down, and it's going to be some sort of a circle, radius to be determined.
Otherwise, it would be z squared.
Right? We want the volume of that guy and the centroid. Now, so let's continue. So how do we, first we have to find what the region D is about, right? So for D, need intersection. So this means that I need x squared plus y squared to be equal to 36 minus 3x squared minus 3y squared, which means x squared plus y squared is equal to 36 over 4, which is what? What?
9.
9. So your D is actually just a circle of radius 3. Which means we're going to think of using polar, but let's set the integral up first. Volume is, if I do, so it's 0 to 2 pi, r goes from 0 to 3. The z goes from the bottom surface, right? So if you're a little man trapped inside this thing, the floor is going to be this guy, which is the x squared plus y squared, which is r squared in polar. And the roof would be this guy, which is 36 minus 3r squared. And then we're integrating the function 1, r dz dr dθ. Right? Don't forget that r that comes with the polar differential. V would be equal to 0.03, and this would be
RZ.
r times 36 minus 3r squared minus r squared dr dθ. So 2 times 0.03. This is 36r minus 4r cubed. So this would be r squared over 2. Coming to that goes 18 minus 1/4 times 3. Okay, so this one is actually 2 times 81 minus 81, so that's just 1 times 81. So that is just 2 times 81 pi. 2 times 81 is 162. That's the volume. For B, note, because it said, what did it say? It said constant density or something.
Yeah, density.
Density is a constant, so note we can use symmetry to our advantage. X bar and Y bar have to be 0, right? Because the region of projection, you'd realize that this is the perfect spot to balance the disk from the XY origin. The thing we don't know is how high up we should go to get that middle point. So really the Z bar is the only thing we need to find. But Z bar is equal to 1 over m times the triple integral of Z times rho. But m is actually what?
Is it
M is 162 pi times a constant, right? Where the constant is just the constant density. And this would be the same guy. Here rho is again a constant. Call it K. Z is just itself. And then we have R, dz, dr, dθ. 0 to 2 pi, 0 to 3, r squared over 36 minus r squared. K actually cancels.
It should be 36 minus 3r squared.
Minus 3r squared. You're still getting the harder finding. This is, now we integral with respect to z, so it's just going to be 1/2 r times this squared, 36 minus r squared minus 4r squared squared. So it's just going to be 1 over 81 times 0.03. And that's what it is. Other questions for 12.6? So this is 23 is actually very similar to a question we did in class, volume of some ice cream cone.
This one gonna be in the test, questions like this, like 25.
Yeah. Like what I just did?
Yes.
Like I'm definitely going to ask you to find the volume of regions with triple integrals or double integrals.
So I'm gonna find the volume and then find the center of gravity.
It'll probably be a separate question centered. I probably wouldn't ask them together, but individually you need to know them. You said 23? draw a picture. What kind of surface is that? Right, just the top half, or no? And this is?
Sphere?
What's the radius?
2. No, square root 2.
Radical 2. That's just a sphere. It's going to hit here at radical 2. It's the x at radical 2. Well, you only care about this part here. Let me make sure what it passed. Find the volumes between the parabola enclosed by the cone and the sphere. Yep. Now, if I had asked you find the volume of the object that is inside the sphere but outside the cone, right? I could have asked that. I could have said the volume of the region inside this but outside that. It means you'd have to find the volume of everywhere out here. And that would sort of be annoying to do given what we currently can do, but in 12.7 we're actually going to talk about a method that would make that easy. Right? As it stands now, we actually need 2 triple integrals to make that work, but we will be able to do it with 1 triple integral when we know 12.7. Just to give you a preview of what's going on. So again, intersection comes down, it's going to be some sort of circle. Radius to be determined. D, we need the intersection, which means I will have x squared plus y squared equals 1. Right? I just plug this guy into here, so I get x squared plus y squared plus x squared plus y squared, which is 2x squared plus y squared, divide by 2, I get this. So D is just a circle of radius 1. Which tells me I can let r go from 0 to 1, theta goes from 0 to 2 pi. So now the volume is the triple integral 1 dt. 0 to 2 pi, 0 to 1. What's your lower limit for the z?
X square root of x squared plus y squared.
Or
Yeah, r.
It's r. And the top?
Is r plus z squared? No, r plus
R squared plus
Square root of r minus 2 minus r squared.
Square root of 2 minus r squared. Okay, so it's 1 times r dz dr dz. And then the rest of it is just doing that integral. It's going to probably be an annoying substitution for that. So it's going to be r times the radical of 2 minus r squared minus r squared divided theta. So this is just going to be 2 pi times integral from 0 to 1 of r times 2 minus r squared minus r squared r. The first one is a substitution. It's going to be something like minus a third times 2 minus r squared to the 3 over 2 minus r cubed over 3. So if I plug in 1 for r, I get minus a third. If I plug in 0 for r, I would get 2 to the 3 over 2 over 3 minus. So that could be one, or I could do something. So what about something like 29 in the second edition, which is similar to 27 in the first edition? Is it exactly the same one as in the first edition?
Yeah.
It's exactly the same?
It's 27. It's first edition.
It's 27 in the first. So now it just says by changing to cylindrical coordinates, but how about you graph the region that this integration is over? How would you do it?
So,
It's a circle.
And it's a cone.
isn't it a cone going up on the positive z-axis cut by a plane that's equals 2?
That's if you look at the
Yeah, that's the summary of what it is, sure. But how do you get there step by step? Well, the first step would probably be to represent the surface using inequalities. How do we do that?
So z goes between root x squared plus y squared up to 2. But x goes between negative root 4 minus y squared and positive quantity. And y goes between negative 2 and 2.
So now you start by, you graph this one. You know that z equals this is just a cone, right? And since z is greater than or equal to that, that's the bottom, right?
Right.
Z equals 2 is just a flat plane, that's just actually the top. So that's just going to cut that off. And it's going to give you a region projection which is down here, which might be equal to this set of inequalities, but it doesn't have to be, right? So just be careful of jumping to conclusions, right? Because they could be mean and put a 3 here, in which case things are,
Oh, I see.
you would be like inside here. You would really,
Right, but with that inequality,
right.
it's a radius.
But with this inequality, this would give you a radius of 2, right? Which is what you get here, right? Because this, it's sort of like you're graphing, this is the same as saying something like x squared plus y squared between 4.
Right.
Right. Because it's a circle where y goes from 2 to minus 2, and the right side is the positive 4 minus y squared, the left side is the negative 4 minus y squared. Which happens to be a circle radius 2, it's exactly the same circle here.
And if it had been a 3 rather than 4, how would that have?
Well, the radius would be radical 3, so there'd be an inner circle here.
Right.
And if I'm asking about the volume of this over that, you would only take this little part in here.
Okay.
Right. That would define your 2 outer limits.
I see.
Yeah, so it's just a cone cut off by a plane, right? That's the, so you're like the little kid whose ice cream fell off the cone. Yeah. Okay, so how would you actually set this up? I'll leave it for you guys to work it out, but just to set it up in polar, in cylindrical coordinates, which is polar coordinates in 3D. So the setup would be what? The integral,
Of -2 to 2.
for, I'm doing the polar coordinate setup now.
Oh, that's from 0 to 2. And then 0 to 2.
R to
And,
2.
and then from R to
This
2.
would go from R to 2, and what would this be?
That would be dz, dy.
Remember, we're integrating xz.
Oh, exit. R cos,
So it'd be R
And Z.
cosine theta times z does nothing, and then it's R dz dr d theta. So it's R squared cosine theta d z dz dr d theta. And note here, we couldn't actually evaluate the cosine first and get that 2 pi out here like we've been doing by habit, because now there's a cosine on the inside. There's a theta in the inside. So we can't actually separate anything. We'd have to, be pedantic about it and do one integral at a time from inner to outer. Do you guys want to take a break now, or?
yeah. Yeah.
Okay, 10-minute break. Then we do spherical coordinates.